Okay. All right. Yeah. So what we're doing is some Linux, mostly vulnerabilities. I did the Spectre attack. As you can see here, we have a couple of pre-steps. We want to put something in memory. So we'll put our string, the secret is 42, into our memory. Then we have a compilation flag, and it turns on lots of flags that we're going to need. You could do them individually, but it would be kind of a long list, so we just do the one. And then once the attack is run, you can see from the screenshot below that if you look at each of the address, you can see that it prints out the secret is 42. So how this happens exactly is that modern CPUs will run pretty much any code they get, whether an if statement checks out or not. And then later on, it checks to make sure before it shows the results, hey, does this actually logically work? So technically, all operations are ran and put into some temporary memory. So how we get this is we get into that temporary memory through some side channels, and then we can print it out, even if you can't see it on the surface from a console.
So the software patch for Spectre isn't really something that's within even our collective programming abilities. So I'm going to talk about Kaiser instead, which is a sort of proposed solution that's still a work in progress. So on 32-bit systems, the layout of the kernel space is the same for both the address space and the user space layouts. Because without this, with like sort of an extra like kernel and user space layout like copied over, the system would run considerably slower. But since the attack is a hardware fault, Kaiser is sort of a software solution to it, which is kernel address isolation to have side channels effectively removed instead of what we've talked about before, Castler kernel address space layout randomization, and that attempts to solve the issue. There are two sets of page tables in Kaiser's proposed solution. There's a kernel space and user space addresses, which is the same as before, but this is only when we are in kernel mode. And then there's this new shadow page table with a copy of only the user space addresses and minimal kernel space mappings. And this will allow most of the kernel's address space to be hidden in user mode. So when a syscall exception or interrupt occurs, the system will switch to kernel mode. And this is much harder to exploit than Castler, sort of a hardened kernel. So there are a few issues with this. Since all programs use system calls or interrupts, a few hundred cycles will be added to like each operation. Performance hits can vary by processor and task, but we have seen between 5 and 30% performance hits, which would typically be unacceptable, but since Spectre and Meltdown have been sort of on the forefront of attacks for quite a bit here, a more hardened lockdown kernel is definitely more than necessary. There is a possibility to allow users to toggle it at runtime to not have the performance hits, but of course you would want to have this on as much as possible. Because these exploits can get a lot of secret information. And it's now implemented in Linux as kernel page table isolation. And the problem with Spectre is, since it is a hardware issue, it is extremely hard to patch by software. And a lot of the attempts have just not gone well. Linus Torvalds has been on record criticizing many of Intel specifically. So Spectre pretty much still haunts us on old CPUs until Intel gets their things together and fixes it at a hardware level.
Oh, I was muted. Up next, we have another really interesting exploit. We got the dirty cow. The dirty cow is an exploit that is in Linux that can be used to gain root access to a system using the race condition being targeted towards the memory system. So how is it done? We map a read-only file to memory using adv don't need. We then use a different string to shoot out proc self mem to access the memory there. We then brute force rewrite to what's in memory until we want to stop. And with the first string being delayed, we will cause a flip flop of the processes that will rewrite to the original non-writable file. And then from this, we could do things like write in a backdoor to root, and then we have access to it. Now, how does one clean this dirty cow? Well, basically the patch, they took madv underscore don't need, and they had it throw away anything mapped to memory if it was dirty being the bit that shows if it's modified or not. If it is modified, it is dirty. If it's not modified, it's clean. So because they throw this out, we aren't able to get the flip flop because it calls a new copy each and every time, thus ending the possibility for the race condition to happen.